Today, our topic is molar heat capacities. Okay, and to understand molar heat capacities, at first we need to understand what is a heat capacity of a system. The heat capacity of a system is mainly the heat required to increase or to change the temperature. In this case, we will only focus on increasing the temperature, not decreasing the temperature. Heat required to increase the temperature of a system, from T1 to T2, where T1 is the initial temperature and T2 is the final temperature. So heat capacity is mainly represented with the letter C, capital C, and it is the heat required to change the temperature from T2 to T1. So it will be a difference between T2 T1. So we can write Q divided by delta T. So this is what heat capacity is all about. Now, what about molar heat capacities? When we are talking about molar heat capacity, we need to recapitulate the idea or the concept of the change in internal energy and change in heat capacity. At first, let us start with the change in internal energy, del E or del U. We can do anything. So del E or del U is nothing but heat change. We can say it is the heat change at a constant temperature and volume, whereas del H can be stated as heat change at a constant temperature and pressure. So heat del E and del E or del U is the heat change at a constant temperature and volume, and del H is heat change at a constant temperature and pressure. Now let us understand it in a more clear way. So we will write that delta E is directly proportional to the QV is directly proportional to QV. Now, when we are going to divide this delta E with temperature, okay, means if we are going to, we can also write it, modify it as del E, dE is directly proportional to QV. So if I write here dE by dt, then we will write here QV by dt as well. Okay, QV by dt as well. Now, dE dt, this change in internal energy at with respect to temperature, change in internal energy with respect to temperature can be regarded as heat capacity at a constant volume. Okay, heat capacity as at a constant volume. So we can write here as CV is directly proportional to QV by dt. So this change in internal energy with respect to temperature is also termed as CV, or the heat capacity at a constant volume. Okay, so heat capacity is the change in when the system heat required to increase the temperature from T1 to T2, and del E is the internal energy change, the heat change at a constant temperature and volume. So heat change means the amount of heat required or the change in heat when the volume is constant, temperature and volume is constant. So here we are writing CV, heat capacity, as a constant volume. So we can write, therefore, QV equals to CV, or directly proportional to CV dt. And when we just put out this, means when we remove or exchange this proportionality sign with an equal to sign, there comes a constant of proportionality, and here it will be n. So we will write QV equals to NCV dt. QV equals to NCV dt. This QV NCV dt will be regarded as molar, okay, molar heat capacity. This is the equation for molar heat capacity. Okay, these are the equation for molar heat capacity. Okay, so here N is the number of moles. N will be regarded as number of moles. So it is for CV, means the heat capacity, molar heat capacity at a constant volume. It can be also extended to the concept of CP, where we will write that QP is directly proportional to del H. That is, Q means heat change at a constant pressure, which is actually proportional to the enthalpy change of the system. So we'll write the same thing, Qp by dt is directly proportional to del H by dt. And now this Qp by dt is directly proportional to Cp. Del H by dt will be Cp. Now Qp is directly proportional to Cp dt. And when we just when we remove this proportionality sign and bring a equal to sign, then a constant of proportionality will come and we will get Qp equals to Ncp dt. Okay, this is also the equation for molar heat capacity here at constant volume, and here it is at constant pressure. Okay, at constant pressure. So these are the two equations for molar heat capacities. Okay, Cp and Cv are molar heat capacities at constant pressure and constant volume respectively. Now, if we have to understand about this, then let us come to this fact that we know from the equation of enthalpy, that H equals to E plus PV. We all know this. So therefore, we will write H minus E will be equals to PV. Now, we will write DH minus DE equals to D of PV. Okay. Then we will do actually, instead of this, we can write this DH dt minus DE dt equals to d dt of PV. Now PV is nRT, because when we are considering it to be an ideal gas, the system is considered for an ideal gas, then we will term PV as nRT. So here dH by dt will be regarded as Cp, dE by dt Cv, and this will be dE by dt nRT. Okay. Now Cp minus Cv equals to d dt. N and R are constant, it will come out, and T will be here. So we will write Cp minus Cv equals to nR. So for 1 mole of an ideal gas, Cp minus Cv will be equals to R, because for 1 mole N will be equals to 1. So Cp minus Cv will be equals to R. Okay, so this is what Cp minus Cv actually defines. From this equation, we will understand a different aspect. We will learn about the heat capacity ratio. So we have Cp minus Cv equals to R. Now we are learning about the heat capacity ratio. Okay, now we are learning about this heat capacity ratio. Cp minus Cv equals to R. For 1 mole of an ideal gas, Cp minus Cv equals to R. Now we will divide all through this with Cv. So we will get Cp by Cv minus 1 equals to R by Cv. Now, this Cp minus Cv is actually the heat capacity ratio. This Cp by Cv is actually the heat capacity ratio and will be regarded as gamma. So gamma minus 1 equals to R over Cv. Gamma minus 1 equals to R over Cv. So in other words, Cv can be written as R by gamma minus 1. Okay, R over gamma minus 1. This we can write. So why this is important? Because when in a few minutes or in a few moments in our next few classes, we will be learning about the work done during adiabatic expansion of an ideal gas. In that equation, when we are going to learn, when we will understand that segment, then we will use this segment and we will find the work done for an ideal gas when they are in adiabatic expansion, when they are undergoing adiabatic expansion. So this is one of the parts, but where this is where will be it will be required. Now, heat capacity ratios are actually important in our exams, because for a monoatomic gas, for a diatomic gas, and for a triatomic gas, these heat capacity ratios are different. And with the help of these heat capacity ratios, we can actually detect them. We can actually separate them or distinguish them. Okay, so heat capacity ratio for a monoatomic gas, gamma, for a monoatomic gas is equals to 1.66. Okay, what are the monoatomic gases? They can be helium, neon, argon. Any noble gas are called as monoatomic. Only one atom of the gas will be there. So any noble gas will be monoatomic gas. Now, gamma for diatomic gases. Gamma for diatomic gases like nitrogen, carbon monoxide, hydrogen oxide, anything that can be there, it is 1.4. Okay, it is 1.4. So nitrogen, oxygen, hydrogen, carbon monoxide, etc. Anything. Okay, so these are diatomic gases. And for triatomic gases, gamma for triatomic gases will be 1.3. Okay, so triatomic gases are ozone, carbon dioxide, water vapor or hydrogen sulfide gas. They can be also be taken as triatomic gases. So these are the values of heat capacity ratios for monoatomic, diatomic, and triatomic gases. So with the help of this heat capacity ratios, we can also find another segment which is known as heat exchange. So next topic will be about heat exchange, or subpart of this topic is heat exchange, calculating the value of heat exchange. So heat exchange will be equals to the heat capacity. Heat capacity, it can be at a constant volume, it can be at a constant Cv or Cp times delta T, change in temperature. Heat capacity times delta T. This is heat exchanger. Again, another thing can be, can be specific mass or specific heat times mass times delta T. So heat exchange can also be specific heat times mass times delta T. So these are all important.